One of the problems that can arise in the process of doing U substitution, that is anti-differentiating the chain rule, is that we'll find pieces of things that are close to what we want, but they don't quite work out. And usually what the difference is, and we actually don't know how to deal with the difference if it's any more than this, is just simply something that involves a constant multiple. All right, so actually let me adjust both of these problems here just a little bit. That looks a little better. So if we take a look at the first example here, obviously there's an x to the third plus 9 kind of inside a power function. And that's a good place to look to find our u. And if we take the derivative of that, we get 3x squared. And if we look at the rest of our integral, we only find an x squared. We don't see the 3. But the 3 is a constant multiple, and it turns out that we can play with constant multiples a little bit. Here's how we can do that. So we have u is equal to x to the third plus 9. du is therefore equal to 3x squared dx. But I could multiply both sides of this second statement by 1/3. And consider 1/3 du is equal to exactly x squared dx. X squared dx is what we have in our integrand, or in our integral, I should say. So we could just replace it with 1/3 du. 1/3 is a constant multiple. Those are things that we can pull in inside and outside of integral symbols. They don't cause any problem. So if we find a piece of our integrand and take its derivative, and it's different by nothing more than just a constant multiple of the rest of the integrand, then we're in pretty good shape and we can deal with things. What does this look like if we continue with the integral? Well, I can pull the 1/3 out front times the antiderivative of u to the fifth du. What did we do there? Well, we replaced the x to the third plus 9 to the fifth power with u to the fifth power. And we replaced the x squared dx with 1/3, which I pulled out front, and du, which goes in the back. Anti-differentiating, we're going to get 1/3 times 1/6 times u to the 6 plus c, which is 1/18 times x to the third plus 9 to the 6th power plus c. Again, go ahead, take the derivative of this, take the derivative of your answer, see if you get back to the integrand. You most definitely will. Here's a similar example on the second one we see here. X squared minus 2's derivative is going to be 2x, not 6x, but the important part's the x. We have an x, we have it to the right exponent. The only thing that's different is that constant multiple. So let's choose x squared minus 2 to be replaced by u. Then du is 2x dx. And since we want 6x, we can multiply both sides by 3. Sometimes we'll use fractions, sometimes we'll use whole numbers, sometimes it gets a little more complicated. It's not a fraction with a 1 in the top, but we can always solve these things and come up with a correct and proper substitution. So substituting, I'm going to get u to the 4th power. That's putting u in for x squared minus 2. The 6x and the dx are going to be replaced by a 3, which I'm going to put out front, and a du. So we're going to get 3 times 1 over 5 times u to the 5th plus c, which is 3/5 times x squared minus 2 to the 5th plus c, after we undo our substitution. Once again, go ahead, take the derivative of your answer here, make sure that you get back to the original integrand. You will.